Okay, this is sample problem 16.8. Calculate the pH of an aqueous solution at 25 degrees Celsius that is 0.035 molar in HI, 1.2 times 10 to the negative 4 molar in HNO3, and 6.7 times 10 to the negative 5 molar in HClO4. So reminder that the pH is defined as the negative log, base 10, of the concentration of the hydronium ion, H3O+, okay? Now, all three acids in this problem are strong acids. And strong acids, what's useful about them in terms of pH calculations is that the initial concentration of the acid, HA for general, is equal to the hydronium concentration at equilibrium, okay? So that means that if we know the initial concentration of the acid, we know the equilibrium concentration of hydronium. Makes it very, very simple. So let's try the first one. The first one is HI. That's definitely a strong acid. I'm going to make a little list here. Let's put a list of all the strong acids just to remind ourselves. So there's the hydrohalic acids, HI, HBr, and HCl. There's nitric acid, HNO3. There's perchloric acid, chloric acid, and then sulfuric acid. Those are the 7 strong acids, okay? So you want to memorize those 7 strong acids. So let's try the first one, HI. So in A, the concentration of HI, 0.035. So that means the pH is just the negative log of 0.035. Remember, unitless. The pH units, there are no pH units, unitless. Okay? So 0.035 negative log of that. So let's come over here to a calculator. Okay, so I'm going to put 0.035. I'm going to take the log of that, log base 10. But remember, it's the negative log, so I'm going to multiply by negative 1. And what does that give us? 1.4559. I'm going to round that to 1.46. Now, the reason I rounded that to 1.46 is that there are 2 sig figs here, 3 and the 5. Leading zeros are not significant. So there's 2 sig figs. When you take the log of a number, the numbers after the decimal point are significant. So there's 2 sig figs there. Okay? Let's try the second one, B. In B, we have 1.2 times 10 to the negative 4 molar HNO3. Again, a strong acid. So that means the pH would be the negative log of 1.2 times 10 to the negative 4. Okay, so 1.2 times 10 to the negative 4. Okay. 1.2 times 10 to the negative 4. Okay. Let's put that in there. I'm just going to equal sign so you can see what that is. That's 1.2 times 10 to the minus 4. We're going to take the log, base 10, and then we're going to multiply by minus 1, I should say. Okay, 3.92. .92 is less acidic than 1.46, right? The higher the pH, the less acidic it is. So what happens is this concentration of the acid is less than this concentration of the acid, so the pH is higher. Remember, as the concentration of hydronium goes up, the pH goes down, right? So 1.46 results from a higher concentration of hydronium. Now let's look at the last one, part C. Same idea here. It's just a little bit lower concentration. 6.7 times 10 to the minus 5 molar HClO4. So the pH is the negative log of 6.7 times 10 to the minus 5. 6.7 times 10 to the negative 5. Okay, so 6.7 times 10 to the negative 5. There it is in decimal notation. We're going to take the log base 10, and then we're going to multiply that by negative 1. And we get 4.17. Okay, again, two significant figures, 4.17. Let's check that. It's a little bit lower concentration in part C than it is in part B, so the pH is higher. Not by a big difference. It's a difference of around 0.25 units there. Okay, so there's our pH calculations.